Namaskar my dear friends. Let us talk about PWM controllers. So PWM controllers are basically used in SMPS design, and these PWM controllers, which is UCC28 series and UCC38 series, are improved version of UCC28C5x series and UCC38C5x series. So the 5x series is bit like advanced version that we will be seeing now. So if you want to have the part numbers, different part numbers are UCCx8C5x. So these x can be replaced with 2 or 3, that is 28 series and 38 series. And we have other parts like 50, 51, 52, 53 up to 59. Okay. So what we'll try to understand is how this particular current mode PWM controller is very useful for our SMPS design, or like in electric vehicles or heavy electric vehicles designs. And the best part is this particular PWM controller is very low cost and low power current mode PWM controller for your silicon as well as silicon carbide MOSFETs. Okay. And as you can see, we have various devices based on the like we have duty cycle, or we have under voltage lockouts. So like what is the voltage range that you want to utilize for that region we have different devices that is applicable. And we have generally two devices, one is 28 series and one is 38 series. Okay. So if you talk about little bit of features in this particular IC, so we have a capability of under voltage lockout, as well as it can be applicable for both silicon as well as silicon carbide MOSFETs. Okay. And the best part is it can work up to 30 volt absolute maximum rating. So UCC28 series was with a UCC28C4 series was up to 20 volt. Now it has been increased to 30 volt. It can work with 1 megahertz fixed frequency operation, and it has like very fast cycle by cycle overcurrent limiting. It has a capability of very good current rating also, like plus minus 1 ampere. Okay. And these are the things. The other part is it has a functional safety capability. That means it can be utilized in your automotive application also. So in automotive application, basically we will be utilizing high voltage battery, right? So to get a 15 volt output or something like that. So that's the reason, like we have, let us say 800 volt batteries in heavy vehicles, and there you will be requiring to utilize your transformer, and those transformer can be like controlled by the silicon carbide MOSFETs to give you an output of 15 volt using a flyback topologies and all. So as you can see very clearly, the applications can be in let's say motor drivers or energy storage systems, or we have solar power inverters. We also can be like utilize this one in our EV charging stations for isolated power supplies, and very much general purpose power supplies it is used for your DC-DC converters or offline isolated power converters. So why do we use this particular converter is because of the functionality as well as very easy to implement. So I have taken lot of designs with my this particular device, which is UCC28C5x, and at the same time this is very low cost device. Okay. So as I already told you very clearly, that let us say we have a UX series device. Okay, so this is our device, and what is the functionality that will be there? We have one output pin that is going to like switch on this MOSFET, and this MOSFET is actually connected to the primary of your transformer, and this is how you are going to get your output. And this is a current sense resistor which will be monitoring the current from your drain to source, and this is my gate driver. So this is the UCC28C5x device, and this output is going to drive your MOSFET based on its switching frequency that is there. So this was all about a basic introduction of this particular device. Let's get into the understanding of how to design a particular switch on SMPS. When we see the particular application diagram, so we have very typical application diagram, as we can see from the data sheet. So actually the data sheet has been extended from UCC28C4x series only to 5.5 series, because 5.5 series is the improved version of 4 series, right? So what happens is we have, let us say, input voltage, and it can be, like directly fed into the power supply. We have V reference voltage, this can be taken out as well, and this is 5 volt V reference, and we have setting of RT and CT, which I have already told you that this can be used for setting the switching frequency of this particular device. So this is oscillator frequency setting, my FOSC, and based on that we will be having SW, like switching frequency, which will be FSOW by 2. Okay, so this is what it will be there. In some of the devices it will be equal to oscillator frequency, and some other devices which it will be equal to half of that. So basic, very simple circuit you can see, and we have to have a requirement of one capacitor at the V reference, and at the same time this is ground pin. We have compensation pin, so compensation pin can be connected to the feedback pin through an RC circuit. Okay, so this like RC circuit can compensate this particular device. At the same time, this particular compensation pin can be used to switch off this particular PWM controller using some comparator. You can do that. So let us say we have a reference voltage of, let's say, 2.5 volt. So whenever my input voltage that is more than 2.5, what will happen is this will be pulled low, and this is how this particular uh, PWM controller can be switched off. So that's the functionality of compensation pin. At the same time, if you come about feedback side, so feedback side, this output voltage can be regulated by utilizing a resistor divider R1 and R2, and generally in isolated power supplies we utilize basically TL431 to set this particular feedback voltage, and at the same time we use optocoupler also, so that we can achieve the isolation between primary to secondary. Okay, coming back to the MOSFET that we are going to drive, which is my Q1 here. So this output is going to generate the output pulse, which will be high and low based on the gate requirement, and this gate will be driven by the output pulse, and this is how we will be getting the switching requirement. Okay, coming back to the device performances. So let's say, what is the device improvement that has happened from UCC28C4x series or UCC38C4x series to UCC28C5x series or 38C5x series. So as you can see, this is the 4x series and this is 5x series. So in 5x series lot of improvement has happened. Okay, lot of improvement has happened is you can see the supply current is very small. Now it is just 1.3 milliamperes. The startup current is maximum 75 microamperes, and the VDD supply voltage has been increased to 30 volt. From 20 volt it has been made to 30 volt. The reference voltage accuracy also is now better, which is just 1% tolerance. So earlier it was plus minus 2%, now it is plus minus 1%. Okay, and we have under voltage lockout and Dmax for silicon FET. So both of them are having 6 options, like UCC40, UCC28C40, 41, 42, 43, 44, 45, 46, something like that. Similar to that for SiC MOSFETs, this is having 6 options. And coming back to the package option, this is very small package. It is available in both the cases. You can see VSSOP package, but other packages are also there. I'll just tell it to you now. If you talk about device information in like 5x series, we are having these many devices of SOIC package and VSSOP package. Okay, so it starts from 50, like 50, it goes up to 55, and then it starts from 56 also, it goes to 59. So we'll see what are the different parameters for this 50 to 59. So if you move to the device comparison table, what is going to happen is, based on the turn on voltage and turn off voltage, so you will need a minimum 14.5 volt to turn on these particular devices, which is going to be 52 and 54. Okay, so that's the understanding we should have. Now if you want to work on a voltage of around more than 8.4 volt, like let's say 9 volt or 10 volt or maybe 12 volt batteries, then in that case you can go ahead with 53 device. So 53 and 55 series can be used for your 12 volt application. So this will be used for 15 volt or more, this will be used for 12 volt or more. Okay, or like up to your 9 to 12 volt. This can be used for just around, let's say, 9 volt or something. like turn on voltage requirement is 7 volt. So 50 and 51 can be used for that many voltage. Coming back to bit higher voltage ratings, let's say if you want to work on 20 voltage or 20 volt or 24 volt ratings, in that case you can go ahead with 56 and 57 series. And similar to that, this is also there for your silicon carbide MOSFET. So you can see that these devices are actually used for suitable for HV applications, like high voltage applications, where you will be needing, let us say, we have 800 volt car batteries or heavy vehicle batteries, and from there you are going to have a battery charging system or something like that. In that case you can utilize 56 and 57 H as well as L both. And in the same manner we can utilize 58 and 59 series device as well. So this is all about this thing. For working with different like functionality, you can see that if you want to utilize it for offline application, then you can go ahead with these devices. For DC-DC application, we can go ahead with these devices 53 and 55, and for battery application we can go ahead with 50 and 51 series. So battery application, it will be a little bit lower voltage, let us say 9 volt battery or something like that. In that case we can utilize this one. If you want to see the junction temperature ranges, then if you want to go ahead with 51, then it will work up to -40 to 125 degrees centigrade, and if you work with 50, then it will be working with 0 to 85 degrees centigrade. So I'll tell you what is the difference between 28 and 38. So 38 is actually going to work from 0 to 85, and 28 series is going to work from -40 to 125 degrees centigrade. That is the only change between 28C series and 38C series. So 38C series has lower temperature range of working, and 28C series has higher temperature range of working. And there is one more difference that is coming between 50 and 51 is 50 is having 100% duty cycle and 51 is having 50% duty cycle. Similar to that, 53 and 55 and 52 and 54 are having 100% and 50% duty cycle. So generally I prefer to have 50% duty cycle for all my designs. So that's the reason, like we are always utilizing either 55 or 54 or 51. And similar to that, we can go ahead with 57 series or 59 series. Anyway, this were actually our design. That's the reason I am telling you, but it is not a problem to utilize 100% duty cycle device as well. Let's get back into the pin configuration. So if you see pin configuration, already we have discussed UCC28C5x series in my previous videos. So in this one also the same pin configuration and everything is there. Either you can understand one more thing is UCC28C55 is actually a direct replacement for 44 series. So that's the best application you can have now. So this we have already understood. Now we'll directly get into the device parameters. So if you see absolute maximum rating, you can go ahead with 30 volt up to 30 volt. So it's nothing to do here much about. So we'll directly get into the next part. Let's talk about recommended operating condition, like up to what voltage range it can take up. So it can take up to 28 volt input. So that's the best part. So generally it can be utilized for your 12 volt application or 15 volt application, or let's say 24 volt application or even 18 volt application. So a lot of different voltage ranges you can now utilize it. Output drive voltage is also equal to your input voltage, which is going to be 28 volt, and you can see average output driver current is 200 milliamperes. If you talk about the junction temperature, so junction temperatures you can see thermal resistance. So thermal resistance is junction to ambience thermal resistance is 128 degrees centigrade per watt for SOIC package, and for VSSOP package it is bit higher. So that's the reason I always prefer SOIC package, which has a better thermal capabilities. Okay. Now let's get into the next part of electrical characteristics. So if we talk about V reference, so as I have told you that V reference voltage will be 5 volt. Coming back to the I reference output, so that will be 45 milliamperes in short circuit condition. You have oscillator switching frequency. So oscillator frequency initially it is 53 kilohertz, and it is just plus minus to 50.5 kilohertz to 55 kilohertz. We have feedback pin. So feedback pin, as you can see, we have 2.5 volt voltage at the feedback pin. So this was all about this. Now let's get into the understanding of block diagram of this particular device. So in this block diagram, what you can see is we have the supply voltage which is going to a enable circuit. So this is my buffer circuit, which is actually nothing but a schematic trigger type, which is having little bit of hysteresis, and this is how this is going to go to enable circuit, and it will generate a V reference output which will be coming out at the V reference pin, which is 5 volt. Okay. Now if we talk about this RT and CT pin, so RT and CT pin will be having one resistor and capacitor configuration. So this is how they will be generating the oscillator frequency for the internal application of this particular switching. So this is the totem pole configuration. Like you can see, we have a PMOS here and we have NMOS here, and then you have this push-pull configuration kind of thing or totem pole configuration kind of thing, and this is how it is driving the output, which is going to drive the gate of the MOSFET, which is going to switch on and switch off. Similar to that, this is my feedback pin, which is actually connected to the error amplifier. So it is error amplifier is nothing but a kind of comparator, you can say, and or you can consider this is error amplifier is making sure the output is regulated properly based on the 2.5 volt reference and the feedback that has been generated from the output voltage. Okay. We have compensation pin. Actually it helps you to reduce the errors or something like that. We have current sense pin, which is going to monitor the current through the drain to source of the switching MOSFET. So switching MOSFET that will be utilized outside, that you have just now seen. Okay, that's all. So this was all about the block diagram of this particular device. Coming back to the simple VDD protection. So what happens sometimes is, let us say we have the VDD supply pin here. So what we can do is this supply pin VDD pin, VDD supply voltage can be actually generated. This is not VDD pin. This is the primary supply pin, which is maybe a high voltage. Okay, high voltage. So this high voltage pin can have one resistor here, and we have one DJ, that is Zener diode. So this Zener diode is going to have a clamping voltage which will save the input. That's how you can save your VDD protection. That is one thing. Another thing is, anyway, this particular VDD supply has been generated from your auxiliary winding. So this auxiliary winding is generating let us say 15 volt. So at the same time, this Zener diode can be utilized, let us say 18 volt. Let's say for 15 volt application, you can have a Zener diode clamp of 18 volt, which will have a good protection for the VDD pin. And this is very simple circuit. I am not going to explain you again. Here itself you can see that we have this particular transformer, which is going to, like switching, let's say in flyback topology, there will be a rectifier diode at the output, and you can see what will happen. This particular primary side is getting switched on because of this particular MOSFET, and which is being driven by this output signal. Okay, so this is how it is working. Understood? So this is my drain and this is my source, and this source drain to source current will be there, which is IDS, that will be monitored through the current sense pin. So this particular RCS, which is going to be have a current sense resistor to go to the CS pin of my device. Okay, so here we have only VDD pin and output pin shown. We have other pins that is also there. One more thing that we have to do is, whenever we have VDD pin, that must be supplied with the bulk capacitor and a smoothing capacitor. So you can utilize, let us say 100 microfarad plus 0.1 microfarad. That is a very good design. Alright, let's talk about how does this hysteresis works. Okay, so you can see we have under voltage lockout capabilities for different devices. So I am not going to talk about all of them, but one of them we will just see. Let us say we are going to choose this device, which is going to be 54, or let us say we are going to choose this 55. Okay, so in 55 what is going to happen is 8.4 volt is switch on voltage and 7.6 is switch off voltage. Or maybe if you want to use 54, then what will happen? 14.5 volt is switching on voltage and switching off voltage is 9 volt. So how does it mean? What does it mean? So what happens is, if you see from this graph, in the first time, let us say I'm going to utilize 28C54, okay, UCC28C54. So you saw 14.5 volt is the turn on time, and let me just see again, 14.5 volt and 9 volt, right? So 9 volt is off. So what is going to happen is, as soon as we supply the voltage of on the VDD, so till it reaches to this 14.5 volt, then only it will switch on, okay. And let's say our VDD supply voltage is reduced to like lower voltage, so it will not switch off until it reaches to 9 volt, okay. So then only it will come down and it will switch off. So supply current has reduced to less than 75 microampere, and this is how under voltage lockout functionality is happening, okay. So what is happening? Very first thing is, it is switching on at, let us say, 14.5 volt or more than that, and then it is continuing its functionality. When it has to switch off, it will not switch off before my VDD drops down below 9 volt, okay. So this is how this hysteresis is working. Let's get into the current sense circuit. So current sense circuit, I told you already, like we will be connecting through the like RCS pin. So one RCS will be there, which is a current sense resistor that will be connected through RC filter to the CS pin. So this is how a very simple connection. And we have the MOSFET. Just now I told you how it was. This is the MOSFET that was there, which was getting switched on, drain to source, and this is my gate. And this particular source will be connected at this particular point, and this is how the current flowing through the drain to source. This is looking like P, so let me make it D. So this is drain to source current is flowing through that, and this current sense resistor is actually monitoring the current flowing through that switching MOSFET. So this is very simple circuit for your current sense application. Why I am explaining like this one by one is, this is the best way to understand, complete understanding, or like if you want to be a very good hardware engineer or design experts in any of the IC design or maybe IC applications design, whether it is a PWM regulator or whether it is any switching regulator or LDOs or maybe any circuitry for that purpose. You have to have an understanding of each and every pin functionalities and what are the different options that they can be utilized. So this is the best way to understand. Coming back to the other circuitry, so let us say oscillator circuit. So oscillator circuit, we need to set the oscillator frequency for the circuit. So in that case, we will be using one RRT and CT. So these two resistors and capacitor will be setting the oscillator frequency, and this is how we will be achieving our switching frequency of the output of this particular device, okay. So this is how it works. We will give you an understanding how to choose the value of RRT and CCT for different oscillator frequency values. There is a graph on that, we will be utilizing that. At the same time, another part is, we can utilize this particular pin to have a synchronization circuit also. So synchronization circuit is nothing but, let's say we have like oscillator frequency or like clock frequency from outside, let us say some microcontroller or FPGA. In that case, that particular signal can be synced to this pin with one 50 ohm resistor that can be in between RRT, CCT and one resistor. So if you have this configuration, then this particular circuit can be implemented for synchronization purpose, okay. Coming back to the next one, soft start implementation. So what happens is, sometimes we want to have the IC to work in soft start, like it should not start suddenly. Let us say it should not start suddenly, otherwise what will happen is lot of ringing will happen, okay. So soft start means it will have slowly start, okay. So this will take little longer time, but it will not have any overshoot or something. So that can be achieved by this particular configuration that you can see here. So what is going to happen is, we are going to have one like NPN PNP transistor at the compensation pin. So at the compensation pin, we are going to have one NPN transistor and at the same time one clamp diode. So this clamp diode can be used to bias this particular base of the transistor, okay. So with this particular arrangements, we will be able to achieve soft start implementation with the resistors of RSS and CSS. So CSS is kind of the soft start timer setting capacitors. Okay. Another part is we can switch off this particular device. As I already told you, either you can utilize one I mean, let us say this is my V input or enable signal, and this is my V reference, and this can be sent to my comp pin, okay, compensation pin. That was one method. Another method was it can be also implemented using a MOSFET device. So what happens is here I can send my enable disable signal. So whenever I send it high, so what will happen, this particular MOSFET will turn on and this will be grounded. So compensation pin will get grounded, and as soon as it gets grounded, what will happen, this particular device will get switched off. So my UCC28C, let's say 54, we are working, so in that case this will get switched off like in shutdown mode. Similar to that, this compensation pin, what it was doing in the op-amp configuration, let us say this is my comparator. So this is my comparator with schematic trigger configuration or like schematic trigger capabilities with some hysteresis. So V reference, let us say we are setting it to 2.5 volt. So as soon as my enable logic goes more than 2.5, let's say it goes high logic, let us say 2.5 volt, sorry, 3.3 volt. So in that case, what will happen, the output will go low and this compensation pin will go low. So this is two ways to design your enable disable circuit. Coming back to the current mode PWM can be also used as voltage mode PWM. So what we are studying right now is, let us say UCC28C5x or 54 for higher voltage and 54 for little lower voltage rating. So this can be also utilized using like in voltage mode. So voltage mode, how you can convert this into voltage mode is, we will have to utilize this oscillator pin only. So oscillator circuit actually can generate one like sawtooth waveform on the current sense pin. So what is going to happen is, let's say we have set our oscillator frequency RRT and CCT to, let's say 100 kilohertz or 110 kilohertz. So my switching frequency can be 55 kilohertz, right? Half of that I am taking. Now to set this particular IC into voltage mode, we will be utilizing one voltage divider resistor. So this voltage divider resistor, let us say R1 and R2, is going to generate one sawtooth waveform. So you can see here it is going to generate 0 volt to 0.9 volt sawtooth safe signal to the input of current sense pin, which is also one of the PWM control comparator. So current sense pin is also having one comparator inbuilt that you saw in the block diagram, and that is how it is going to get converted into very easily from current mode to voltage mode. So voltage mode are generally like preferred in many control application for variety of reasons. Okay, so that we are not going to talk about right now, but but voltage mode applications are used. So alright, this was all about this particular like understanding for different configuration and different parts of the circuitry for this particular device. However, coming back to the RRT and CCT pin that we had already discussed in the previous designs, so this is the switching frequency setting curve. So in this particular typical characteristic curve, you can see that this is my oscillator frequency, and this is the RRT resistor values that can be set for different values of capacitance. Okay, so we have 5 values of capacitance. Whichever value if you want, you can choose it, and accordingly the resistor value will change based on the diagram. So let us talk about one example. Let's say I choose it 1 nanofarad capacitor. So 1 nanofarad capacitor, this particular color curve you can choose this one. Okay, and let us say we want to set it for 100 kilohertz. So what will happen, this particular 100 kilohertz we can go ahead. So we can see this is the cut point. So this cut point will be actually plotted down, and you can see it is going to come between like this is my 10 kilohertz line and this is 20 kilohertz. So between 10 to 20 it is around 15.1 kilohertz or some 15.1 kilo ohm. So you can use this particular value, which is can be as long like as high as long as 50 kilo ohm or something like that. Okay, So we can utilize this particular value for 100 kilohertz or 110 kilohertz, I think almost, which is 15 kilo ohm and 1 nanofarad. Alright, so let's get into one of the very quick application circuit to close our discussion. So in the previous session we had taken with UCC28C44 or 38C44. In that also the same application design was there, so there is nothing changed. Same thing can be actually utilized, and just the device can be replaced with UCC28C55. Okay, so this was very simple design, as already you know that we have to have our VCC supply pin. So this VCC supply pin voltage will be given from where? This particular, let's say, auxiliary primary input. So this is the transformer that we are using, and this transformer is used in flyback converter mode, flyback topology. So this flyback topology is giving you an output of 12 volt output and 5 volt output, and we have here AC input available. So at AC input we have the fuse and MOBs and all those things, and PTC to have some safeties, and a transient suppression, all those things we can utilize. That I'm not going to get into very detailed one. Why? Because we already know how to design this particular AC to DC converter. After the rectified voltage from bridge rectifier, it is going to go to bulk capacitors, and then we have RCD snubber at the primary, and this particular transformer will be switched on or switched off based on this particular Q1 MOSFET. So our main target is to have this switching application from my device output of this device to switch on this particular MOSFET Q1. So this is the gate of the MOSFET, drain of the MOSFET, and this is the source of the MOSFET. Okay, so whenever this particular output goes high, what will happen is this particular MOSFET will get switched on, and this is how there will be a current flowing through this particular MOSFET, which is IDS, that will be sensed through this RCS. Okay, so current sense resistor is there, which is going to go to RC filter through that CS pin. So this was one of the method to monitor the current sense resistor, right? Another thing is this particular output is not directly fed. We have RD snubber circuit, which is going to reduce the output any like overshoot or something at the gate. So that's the reason we have used here RD snubber, and this is just a voltage divider circuit that can be used to have a proper voltage value at the gate. Okay, coming back to other part, we have reference voltage. So you can see reference pin is supported with one of the capacitor. At the same time, VCC pin is also supply pin voltage is coming from auxiliary winding. So this auxiliary winding is setting the voltage level to, let us say, 15 volt for C54 series. Okay, and this 15 volt can be fed to this particular VCC pin with one capacitor. One more capacitor I'll suggest you to utilize, let's say 0.1 microfarad, and at the same time 0.1 microfarad additional capacitor can be used as V reference pin also. Okay, coming back to other part, which is going to be oscillator setting frequency. So oscillator setting frequency will be RRT and CCT. So this is R6 and this let us say C6. Okay, so R6 and C6 can be used to set the oscillator frequency, as just now I told you how to find the values for different oscillator frequencies. Coming back to this feedback pin, so actually right now it is converted based on the optocoupler. So as you can see, we have the outputs 12 volt and 5 volt, and they have been having a voltage divider of R56, not R56, we have R53 and R52 and R54. So this voltage divider is going to a a voltage reference, which is, let us say, TL431, and this TL431 can set your feedback voltage, and it can be transferred through the optocoupler. So this optocoupler can be utilized very easily, and this optocoupler is setting the compensation to regulate the output voltage to 12 volt and 5 volt. So this was all about the particular schematic design. We have one more application that is given in the datasheet itself. I'll just explain you that as well. So this was very simple. Let us say it is actually given in terms of UCC28C42. So basically I already told you, like UCC28C4x series is same as UCC UCC28C5x series. Okay, so this 5x series device also can be used at the place of 4x device with improved functionalities. Let us say higher voltage range capabilities and lower, current consumption and all these things. Okay. So this is a bit complex, but however our main purpose should be what is my supply voltage, what is my output, how it is driving the gate of MOSFET. Okay, so you can use one RD snubber here also same way. Okay, we are using here Zener diode to protect the supply voltage. So you can see like I have used here 18 we have used here 18 volt Zener diode to protect the supply, and you can see here feedback pin is used now, and at the same time we have slope compensation also, like we have soft start timing. So you can see we have C ramp, that is CSS and RSS. Okay, so these two are going to have a soft start functionality, and at the same time we have 15.4 kilo ohm and 1000 picofarad, that is 1 nanofarad. So I think it is working at 110 kilohertz of oscillator frequency. Okay, so this is how this has been set, and that RRT has been connected to the V reference pin. That was another part. You can see we have compensation pin. So this compensation pin has been designed with this particular transistor and the capacitors, and oh sorry, we have this CSS and RSS is here actually. So these two are going to set the soft start timing, and these are ramp capacitors and resistors. Okay, so this was all about this. Coming back to the secondary side, so you can see we have this optocoupler. So this optocoupler is going to have the feedback voltage transferred from secondary side to the primary side, and this is how it is going to maintain. Okay, so that's all. This was all about this, and as I already mentioned you, this particular TL431 is a voltage reference, and this voltage reference is primarily used in various SMPS design. Anywhere if you see, you can blindly utilize TL431. So if you have a particular requirement of, let us say, what is the voltage range that is there, let's say whether it is AC to DC, AC to DC converter, or let's say we have DC to DC converter in automotive application, like let's say in battery charger application we have 800 volt to, we are going to reach to 15 volt output, in a traction inverter or something like that. So basically this particular device is used in traction inverter, where we need to have a very easy design, very simple design. At the same time we have to have low cost design implementation also. So you can put down your queries in the comment box, and we shall be able to give you exact answers based on the requirement that is required. So thank you so much guys. Bye.